Let's start off with a refresher on vector addition and subtraction. So to start off, we're just going to take some different vectors, add them together, and find the total resultant. Our first one is a pretty straightforward one. We have 15 meters east and 12 meters west. Notice in this case, this is actually a 1D problem. The two directions are opposing. If we want to draw this, we can draw D1 as 15, and I'm going to draw D2. Remember, we add our vectors tip to tail, so where that ends, our next one starts. And it's shorter, so I'm not measuring exactly, but I'm trying to keep them in scale. D2 is 12, but notice it's going left or west. D1 is 15, but it's going right, positive. Now, let's just make east positive. If we want to find our resultant, we'll call that dr. That will be 15 meters plus negative 12 meters because we're going in the opposing direction. That tells us that our resulting displacement is 3 meters. And we do want to put a direction back on this because it originally was a problem with a direction. That's going to be 3 meters east. Most basic case. Okay. Knocking it up to be slightly more difficult, we're going to add together two forces. We have the first force, which is 45 newtons north. And again, I'm not measuring exactly to scale, but I am trying to kind of keep it relatively scaled. So if my first vector is 45, my second vector is about half that much, I should keep that in mind when I'm drawing. And that is 22 newtons west. Okay, notice to find the resultant for this, we're going off at an angle, so we know we're going somewhere northwest, but we don't know exactly what that angle is. We'll need to find that too. So there's two things we can use for this. The first one is Pythagorean theorem, a squared plus b squared equals c squared, because we know we're moving at a right angle with the north and the west. And then we're also going to use trigonometry to find that angle. If you'd like, take a moment to pause the video and try and find those on your own. All right, I'm going to call this D. Again, it's our resultant, so we'll do a dr. Dr is going to be the square root of 22 squared plus 45 squared. And for now, I'll just find the magnitude. This is where sig figs come into play. Because both of these numbers have two sig figs, my answer should also have two sig figs. However, if I was calculating, I would want to keep more decimal places, so 50.0899 ... If you're going to calculate this, either keep the exact answer on your calculator or keep enough decimal places that you're not prematurely rounding. However, for your final answer, you're then going to round to the correct number of sig figs, and it will be 50.0, but we just want two sig figs, so it'll be 50 with a decimal after it. That's going to be in newtons, and I do need a direction, so let's go back to that angle. We can use tan in this case. Tan theta is equal to our opposite, 22, over our adjacent, 45. And you can solve for theta. And that's going to be 26 degrees. So we'll say 50 newtons, 26 degrees west of north, because you'll notice we're mostly going north and then a little bit to the west. Now those are kind of the two basic cases that we're hopefully already pretty familiar with. Sometimes we're going to have vectors that aren't opposing each other and don't make a perfect right triangle. This is when we will need to use sine law and cosine law. You can take a moment to fill those in. And let's take a look at this example. We have a Zeppelin flying at 15 kilometers per hour, 30 degrees northeast for 2.5 hours. It then changes heading and flies at 20 kilometers per hour, 70 degrees west of north for 1.5 hours. And we're trying to find its final displacement. So keep an eye out on what you're actually looking for. As much as it's giving us velocities and times, we actually want a final displacement. But as a reminder, we can calculate displacement using velocity and time. Now, what I would normally do is take a look at each of these and kind of just figure out what can I find. Let's just start off by finding the value for our displacement, and then we'll put them together and add the vectors. So our first displacement is going to be the first velocity times the first time. That's going to be I have kilometers per hour and I have hours, so I'm okay to multiply those together. I know ideally we would like meters, but we're just going to end up with really big numbers. So for now, we're going to leave it as kilometers. 15 times our time, which is 2.5. So that's going to give us 37.5. And this is where I am keeping those extra decimal places. I'm not rounding my sig figs yet. And I'm also keeping my unit so I remember that that's in kilometers, because that could make a difference somewhere. Let's do something similar with D2. D2 is going to be 20 times 1.5. So that's 30 kilometers. And this is where the vector addition comes into play. What I want to do is take each of these vectors and then add them tip to tail. So I'm just going to copy my first vector. To show where the Zeppelin goes first. And then I'm going to copy my second vector. But I need to place it so that I can see where they are going. And I can see that overall, the Zeppelin does go up. But notice I don't really know the angle there. I don't know what direction it's going in. I'm going to call that my resultant. And I'll just label D1 and D2. I do know angles for my original. If I take a look at D1, it is 30 degrees from the horizontal. Be really careful that you don't put an angle in there, because that's not going to be a right angle necessarily. In this case, it looks like it's definitely not a right angle. But let's look at D2. Now, D2 actually gave us this angle there as 70, so that's going off the vertical. But that tells us that off the horizontal, that's going to be 20 degrees. So if I put in a little horizontal here, then I can put in a 20 degrees here. And also, because I know that that angle is 30, I know that this angle is 30 degrees. So that gives me that whole angle inside the triangle as 50. That tells me that for this triangle, which is not a right triangle, I know two of the sides and one angle in between those two sides. That's the perfect case for cosine law. Okay, let's slide this up so we have a little bit of space to work, and let's write out our formula for cosine law. So I'm going to write it using dr, d1, and d2 first. Dr squared is equal to d1 squared plus d2 squared minus 2 d1 d2 cosine 50 degrees. Okay, and then I want to substitute in my values and solve for dr. I'm okay with taking a square root in the same step, so I'll say dr is equal to the square root of, instead of d1 squared, that's going to be 37.5 squared. And notice that I'm keeping all the decimal places there. Plus 30 squared minus 2 times 37.5 times 30 cosine 50 degrees. Pause the video to calculate that for yourself, and when you come back, hopefully you have 29.33 kilometers. Again, this is too many sig figs. I'm definitely going to be rounding for my final answer. But right now, I may actually use this number. In fact, I will use this number because I need to find an angle. I'll call that alpha for now. I need to find that so I can eventually find the direction of dr. And to calculate, I want to use as many decimals as possible. So again, either leave it in your calculator or keep extra decimal places. Now to find that angle, I can use sine law. So I can say that sine alpha, the angle I'm trying to find, over the side across from it, which is D2, is going to be equal to the only angle I know, sine 50 degrees, over dr. And this is why I want to have the extra decimals for dr. Okay, knowing all that, we can say that alpha is equal to inverse sine, let's cross multiply this, d2 over dr times sine 50 degrees. Let's fix that R. And why don't you take a moment to substitute in the values and find that angle, which is equal to 51.59 degrees. This is where I would probably just say that alpha is 52 degrees. Now, keep in mind what your actual angle was. So let's go back to our diagram, and I'm just going to point out this angle. If we start east and then we head north, it's going to be 30 degrees plus alpha. So don't just use that 52 for your final direction. We need to say that it is going to be 82, the 52 degrees plus the 30 degrees. And whatever that is, it's going to be north of east. So our dr is 29.33 kilometers, but now I'm going to put in my sig fig. So dr is 29 kilometers. And as a direction, that's going to be 82 degrees north of east.